I'd like to introduce Scott Mitchell. He's the founder and CEO of Stud.io, a computational construction company. Scott works to bridge Stud.io's software development with its project consulting, enabling some of the most complex projects being built today. Before founding Stud.io, Scott worked as a software engineer at Autodesk as part of the AEC Generative Design Group. While working there, he had access to Howick roll forming machine, which he experimented with in his free time before ultimately leaving to focus on the development of Stud.io full-time. Scott studies and practices film, music, architecture, and computer science, in other words, making things. He enjoys composing for the guitar, producing videos and animations, and experimenting with software development and fabrication research. For the past several years, he and his wife, Brianna, their son, James, their daughter, Frankie, and their golden retriever, Lou, have lived a modern nomadic lifestyle, living in various cities like Boston, Laguna Beach, Austin, and Tulsa, Oklahoma, where Scott is from, and that's where they currently live. So if you haven't noticed, Scott is a bit of a Renaissance man. He's a lifelong learner and a terrific resource for always asking, what if? Scott.
Well, thank you all very much for being here today. I am excited to be at my third Steel Horizons, and what I want to talk about today is the ideas of simple and complex in construction, and what do we mean by that. So here you can see a range of stuff that we've built with our software, a wide variety of things. So if you're not familiar with Stud.io, we got started and our bread and butter has been these complex projects. I'm going to show you an example of that. But there's a lot we've learned about process working on these complex projects that we're now shifting focus to what we can do for 99% of projects that are getting built that don't look like crazy. So when we talk about complex projects, we generally mean complex geometry. So a lot of the projects that we've gotten brought into, they are entirely bespoke geometry. So they're going to need a ton of custom detailing, and we develop systems and processes to automate the fabrication, assembly, the interaction with other building components. These are laser cut steel ribs, which are going to come back in a second. Making sure that all the alignment holes are generated by the machines between different parts, and then also making sure there's an efficient install process in place as well. So that's what complex looks like. When we talk about simple, I think what we really mean is most buildings where in terms of the framing, you want to just automatically populate framing across your project, and then you want that project or that framing to automatically adapt to design changes and coordination as the project progresses. So that's what we mean when we talk about simple and complex. And where I want to arrive at in this talk is that maybe it doesn't make sense to call projects simple, because maybe inherently construction is just complex. And instead, I think it makes more sense to think about simple and complex processes. But we've really spent a lot of time thinking about process, and we have to sort of reinvent process for every project, for these highly bespoke projects. So I want to go through an example of that. This is this museum in Los Angeles. This thing has been under construction for 5+ years at this point. Actually, the very first project that Stud.io ever worked on was this project, but we were called back in last year because they had the scope on the roof that was projected to go like a year beyond schedule. So they wanted to see if there was a more efficient system they could use to get this thing done in time for the building to open. So we're going to look at the roof ribbon, which is this thing that undulates, that goes around the whole building. There are 195 unique panels in the ribbon, all of them a different shape. Every single stud, I think there's tens of thousands of different studs coming off the Howick machine, and also ribs off a laser cutter. It's like 15 engineering types. You can see the variation in geometry between all these types. So we want to come up with a process that's going to automatically generate all the framing, automatically generate all the steel ribs, make sure they're all connected together, make sure this thing's going to get installed on site and make exactly what the architect designed. And we got to do it fast. What this system looks like is we start with what we call the primary frames. So if you're familiar with Howick construction, this is like a pretty typical thing. This is a planar frame, although the geometry looks a little bit unique. So each one of these primary frames was a different shape. And then when we have what we call the secondary frames, attach a primary frame to the next primary frame, basically. And every single frame has alignment holes to the next one. So you just bring two frames together, line up the holes, put a screw in it, and this thing takes on the exact shape that's in the model, which is super important because the Howick frame ends up being sort of like a jig for these laser cut ribs. So there's holes laser cut into the ribs, there's holes punched on the Howick, and those ribs just kind of go and get screwed into the framing. And then we bring in what we call secondary ribs that just slot into the primary ribs and generate the finished shape of this in high resolution with those steel ribs. So that's what a finished panel looks like in the shop, panel frame, I should say. And when we get on site, we want to think about the install process as well. So the same time the panels are being fabricated, we installed these, what we call the rails. So these are also digitally fabricated, so we control the design process for a tube laser to cut all these out. We get all those installed on site, and then we use robotic layout to identify points on the rails and just set the panels down, line up the points, and that thing's going to be in the exact right place. And it worked. Like this is a culmination of years of thinking about how to really efficiently take an architect's geometry, get it built, and get it installed to match perfectly. So we were held to an 1/8" tolerance on this, which we were able to meet, which is pretty crazy given the geometry that we're looking at. And I think most importantly, we were able to get this system installed in about 6 months sooner than the original system was projected to take. So after they get all these panel frames installed, they put a mesh on that, and they come back and put the plaster on. And it looks pretty cool. I think this building is supposed to open next year, I believe. So this is like the first project we ever did, and also one of the most recent. And increase in our efficiency from design to fabrication from the first to this most recent scope is kind of crazy, and it's because we think incessantly about process. So when we get started on a process, we think very carefully about how information is going to flow through the project. So we start with information from an architect. We have design surface. We have the planes that they're going to divide up the surface into panels. So we use that to divide up, to generate the single panel surface. From the joint planes, we generate these primary structural planes. Those primary structural planes plus the surface come up with these primary frame extents. Based on engineering details, we generate the secondary frames. We use our stud finder software to generate the axes of all the studs. There are secondary planes for the ribs. We use those to generate the axes of the ribs, so just lines basically. And then we use our stud finder software. It takes an analytical model and it automatically generates all the fabrication information for the ribs and the studs. This is a repeatable process. So you plug in different inputs, you get the outputs. So 195 panels went through this process. It's an automated thing. You get back engineering information. We get back the files for the Howick. We get back drawings to assemble the Howick, laser cut files for the ribs. So I think the super important thing that I want to stress is that when we work on a project, we don't work on the project, we work on a process that's going to work on the project for us. So yeah, we could run this in 195 panels through this and just get different outputs. You can see the variation that's produced. And these are not just models. That is all the fabrication information and assembly information to get that built. I think this focus on process over projects is the engine that has propelled Stud.io. So we have two sides of the business, and we're sort of unique in this way that we develop and license software. We also work really closely with our clients and get deeply involved on projects. And we have a ton of ideas for things we want to do with the software. And every project is an opportunity to develop that idea, test it on a project. Through the course of a project, we come to find out if ideas are good, if there's parts of an idea that need refinement, if we need to improve the software in some way. A lot of ideas lead to other ideas. So that feeds back into the software. And any investment in the software and in the processes benefits not just the current project, but the one after it, all of the ones after it. So we built up this software and this understanding of how to build processes that's just increasingly efficient, particularly for these complex projects. But a couple years ago, we decided, we've done a lot of these kind of complex projects. That's like a small fraction of the buildings that are being built today. We want to help propel the entire industry forward. So we've very intentionally been developing software and working on projects for simple construction. And I think that term is maybe not the right term, and we'll get to that. The biggest difference between these types of projects, maybe not the biggest, but one of the big differences is the design budget. So with these high-profile complex projects, there's an understanding that the design process is going to be custom. It's going to take some time to put that together. With most buildings, you don't have that luxury. So we've been developing tools to make the process of putting together the process and the system for a project really, really quick. And this is our frame generating tool that we call regions and recipes. So a recipe is a set of instructions. And we want it to work for any panel, whatever size and shape it is. So we have some input, which is just the shape of the panel you want to make, and then we have these instructions that we call strategies that do things like add vertical members, you add members around edges, and that gives you your panel. So this is like the most simple recipe you could ever create. You can add conditions to strategies, so you can put different types of profiles on the top and bottom for tracks, on the sides. You can add details to edges, headers, stud packs, things like that. You can change the conditions for where those are going to occur. You can add parallel members in multiple directions, and then you just give it a shape, and it produces the fabrication information for that shape, whatever it is. And it's just a series of very simple steps. And you just kind of plug and play these things. You can rearrange the order. You get different results. One of the more important features is around openings. You typically have a lot of different specific details that need to occur there. So we have what we call an opening strategy, which allows you to put details around openings, jambs, headers, trusses, whatever. Those depend on certain conditions. So you can sort of codify the engineering details that need to occur in your framing as a recipe and just let that work for you, whatever the shape is. And again, this is not just producing a model. This is click export. You've got the fabrication information for the go to the machine, and you've got your assembly drawings in a second. One click of a button, whatever the shape is, even if you wanted to build something crazy like that. And this is what it looks like to use it. I recorded myself playing around with one panel for like a minute, and it's fun. It's like playing a game. I think the ability to test out different shapes, test out different details, and get an immediate fabrication model back and see what all the different punches and stuff look like is like fun. It's like super satisfying to play around with. And you probably would never build something like this, but you could. Like at any point, you could literally take what you're screwing around with and go build it on the machine, like an hour. You'd have this thing built, which I think is a really exciting feature for being able to test out new ideas, which is something that we really believe in. So that's one panel, which is cool. But what really matters is when you apply these recipes across the project. So these are some early versions of a floor plan and a roof generator that we put together. You give it what kind of recipe do you want for what kind of walls. You can change the floor plan, change the various parameters of the recipes, automatically have it panelize. And all of these things, again, are fabrication ready at every single point. And then you can feed that into other workflows like stacking, and just instantly see what your fabrication, what the actual structure is going to look like for any given input. So that's a fun little animation, but this also has a lot of value for actual projects, in different environments. So in Revit, for example, we can take a whole floor, and in this floor, there's 4 different wall types. We can prescribe a certain recipe for each wall types, and it goes through and generates all the framing for this floor in about 5 minutes. And these are going to be like tracking changes to the walls throughout the project. So you can add a door, and whatever sort of header and jam conditions or opening conditions are prescribed for that recipe, it'll automatically generate those. You can draw in little openings, maybe for an MEP pass-through or something like that. Yeah, so basically, you don't need to think about framing anymore. You just model your project, and the system that you set up beforehand does its thing. Because we don't want you to like modeling framing. We want people to think about designing the systems that are going to model their framing for them. We can run the same thing in Rhino. This is the exact same project. Interestingly, Rhino takes 30 seconds to do it. But there's some of the other interesting things you can do with regions and recipes. You change the recipe that a particular frame is run by. Let's say you need to add a header to the bottom of this panel. And a very critical part is that you also want to manually intervene every once in a while. So you can take one of these things, you can draw in new studs, copy studs around, trim studs, add and edit operations. But like all of the connection detailing is just done for you. Our fabrication solver understands what sort of connection detailing you want, and it automatically deploys that. So, super powerful tool that we're really excited about, and we're bringing this to more typical building projects in the 99%. But what I love about it, like one of the maybe more academic ideas here that has run through a lot of what we've developed at Stud.io, is that simple rules can produce complex systems. You just have a simple, 6-step recipe that produces all of the fabrication information for your panel, or for 1,000 panels. It's the same idea if you've seen any of our presentations before. This is how we think about the more 3D bespoke structures that we do, where we give it the connection detailing that we want applied across the project, and our solver automatically figures the rest of it out. We want to play with just the simple components of our system and have intelligent software that actually deploys that across projects. So that's what we want to develop for users, that we want users to be spending their time developing recipes, developing their systems, and let those do the work for them. In other words, we want them to think kind of like we do. We've found that investing most of our time in processes that benefit future projects is compounding value. So maybe every company isn't developing software, but all these construction companies are developing systems, and we want to give people the tools to develop their own systems, let the systems do the work on the projects for them. So I think, in conclusion, construction is inevitably complex. I think us calling any sort of building simple was a somewhat naive thing. What's more important is simple processes that can manage that inevitable complexity of construction. So in other words, we don't want people to spend time making models. We want people to make processes that make models. Thank you.
Do we have any questions for Scott? Go ahead.
Is that for sale right now?
Yeah, we're in beta right now. So the reality is that like I said, we work closely with our clients. So yeah, you can use the software now. We like to help understand exactly what you're going to do with it, and there may be certain features that we want to improve upon for you.
Are you letting some of these parametric processes drive efficiency in those models? So are you able to look at design intent from architects and then create the most efficient framing for that?
Yeah, not in a generalized sense, but we've certainly experimented with that on isolated conditions. Are you familiar with Grasshopper?
Yeah, very.
Yeah, so we can set up workflows for specific things that we want to optimize. I think there's a lot of interesting potential to bake that actually into the software and have recipes think about things like minimizing material while still satisfying certain engineering criteria.
Amazing. Congrats.
Thanks.